In this video, we're going to talk about the difference of perfect squares, or a difference of two squares, which is a special type of factoring. But before we do that, I would like to take a minute to identify some of the perfect squares that you'll run across the most often. And since I'm only going to be doing the odds for you, I'm going to go ahead and write them over here in this empty space. These are perfect squares that you are more than likely going to run across. One is the number 1 squared. The number 1 squared is 1. The number 2 squared is 4. The number 3 squared is 9. The number 4 squared is 16. The number 5 squared is 25. The number 6 squared is 36. The number 7 squared is 49. The number 8 squared is 64. The number 9 squared is 81. 10 squared is 100. 11 squared is 121. 12 squared is 144. And then 3 more. If I take the letter x and I square it, it becomes x squared. If I take an x squared and square it, it is x to the 4th. If I take an x to the 3rd and square it, it becomes x to the 6th. Pause the video if you need time to write these down. I want you to make sure that you familiarize yourself with these squares, as they will occur more than anything else. Let me scribble those out since we're not going to need them for our video. All right, now what I want you to know is that when we see the number 25, I need you to know that that is the number 5 that was squared. When you see the number 100, that is a 10 that was squared. When you see the number 64, that's an 8 that was squared. When you see a 49, it is a 7 that was squared. These bases are what you're going to need to be able to identify. If you see an x to the 4th and you're working a difference of perfect squares problem, you know that it was an x squared that was squared to get there. That's what I'm talking about with the bases. All right. Now, let's look at our examples. Again, pause the video and write those down if you need to, and be familiar with them. Now, when you're factoring a difference of two perfect squares, it has to have the difference, which means that has to be a minus. Okay, this qualifies. I've got exactly 2 pieces and the middle sign is a negative. That has to be the case. Next, we want to identify what bases are being squared in each position. The number 49, if you remember back to our little list that we built over here, that is a base of 7 that was squared. The b squared, well, if I have an x squared, it was an x that was squared. So if it's b squared, it was a b. And the 25. When I see a 25, I know that that was a base of 5 that was squared. All right, it is a difference and it is 2 perfect squares. So to factor this, you open up your 2 parentheses factors. The first base that you identified goes in each of the first positions. The second base goes in each of the second positions with a plus and a minus between them. The plus and minus have to be there so that we have the middle and outer, the middle terms cancel. And you'll see what I mean when we do a check in a later example. Right now, let's look at number 3. I don't see anything in common all the way across. We still want to check for a greatest common factor always. Now, 120, first, this is a negative, so check. That's supposed to be. The base being squared in the last position is a 5. Is this a perfect square? Yes, that's the number 11. And what number is being squared to get n squared? An n. Because you have a difference of 2 perfect squares, we know that this is a difference of 2 perfect squares. We're going to open up our 2 parentheses terms, our binomials. The first base goes in each of the first positions. The second base goes in each of the second positions, one with a plus and one with a minus. Now, does it matter the order? No, as long as your two parentheses terms are exactly the same, it doesn't matter what order they're in. And we're done. Let's look at the next one. 169n squared minus 81. Well, we've got the minus. That's the one important part. If it were a plus, you can't factor it as a difference of squares. Now, what's being squared in each position? I don't have this one written down, but 169, I believe, is a 13 that's being squared. The number being squared here is an n, and the number being squared there is a 9. I'm going to open up my two parentheses. Our first base goes in the first positions. Our second base goes in the second positions with a plus and a minus between them. Now, let's do number 7, and I'll check this one with you. It is a difference. The number being squared in the first position is an 11 and an m. Number being squared in the last position is a 7. Since it is a difference of two perfect squares, we can open up our two parentheses factors. First base goes in the first position. The second base goes in the second position of each term, and we put in a plus or minus. Now let's check and see why that works. And again, we're not going to do a check on all of them, just when we need it. I'm going to start by just doing FOIL there. I'm going to distribute the 11m onto the second parentheses. 11m times 11m is 121m squared. 11m times negative 7 is negative 77m. When I finish with the 11m, I'm going to scoot over now and distribute the 7m onto the second parentheses. 7m times 11m is positive 77m. And 7 times negative 7 is negative 49. Notice that the two middle terms cancel. That's why a difference of two perfect squares factors the way that it does. I'll see you in the next video.